Welcome to this presentation. Today we are going to discuss about the routing and routing protocols. Delivery refers to the way a packet is handled by the underlying networks under the control of network layer. Forwarding refers to the way packet is delivered to the next station. And routing refers to the way routing tables are created to help in forwarding. Routing protocols are used to continuously update the routing tables that are consulted for forwarding and routing. And now let's discuss about the common unicast and multicasting protocol. The network layer supervises the handling of packets by the underlying physical network. The delivery of a packet to its final destination is accomplished by using two different methods of delivery called direct delivery and indirect delivery. In a direct delivery, the final destination of the packet is a host connected to the same physical network as the deliverer. Direct delivery occurs when the source and destination of the packet are located on the same physical network or when the delivery is between the last router and the destination host. The sender can easily determine if the delivery is direct. It can extract the network address of the destination and compare this address with the addresses of the networks to which it is connected. If a match is found, the delivery is direct. If the destination host is not on the same network as the deliverer, the packet is delivered indirectly. So in an indirect delivery, the packet goes from a router to router until it reaches the one connected to the same physical network as its final destination. So the delivery always involves one direct delivery but zero or more indirect deliveries. The last delivery is always a direct delivery. As I said earlier, forwarding means to place the packet in its route to its destination. So forwarding requires a host or router to have a routing table. When a host has a packet to send or when a router has received a packet to be forwarded, it looks at this table and to find the route between the particular node and the final destination. So the simple solution is impossible today in an internet network such as the internet because the number of entries needed in the routing table would make up the table lookup inefficient. So several techniques can make the size of the routing table manageable and also handle issues such as security. And those methods are called, for example, next hop method versus route method, network specific method versus host specific method, default method, and so many methods are available. So in an internet, the goal of the internet or network layer is to deliver the datagram from its source to its destination, or it may be sent to several more destinations. So if a datagram is destined for only one destination, then we have unicast routing. And if the datagram is destined for several destinations, that is one to many delivery, we have multicast routing. Now let's focus on unicast routing. The unicast routing, a packet is routed hop by hop from its source to its destination with the help of forwarding table. The source host needs no forwarding table because it delivers the packet to the default router in the local network. So the destination host needs no forwarding table either because it receives the packet from the default router in its local network. This means that only the routers that glue together the network in the internet need forwarding tables. So with this, routing a packet from its source to destination means routing the packet from the destination matter that the router connected to the destination network. Although the packet needs to visit the source and the destination routers, the question is what the other routers the packet should visit. You can say that there are several nodes in a packet. The nodes routers that a packet can travel from the source to destination, and what must be determined is which route the packet should take. There are many available routes between the source and destination. So our aim is to select one route which connects the source and destination with the shortest distance. So that is our main aim. So to find the best route, the internet can be modeled as a graph. A graph in computer science or is a set of models or set of nodes or edges that connect the nodes. To model an internet as a graph, we can think of each router as a node and each network between the pair of router as an edge. An internet, in fact, modeled as a weighted graph in which each edge is associated with a cost. If a weighted graph is used to represent a geographical area, the nodes can be cities and the edges can be the roads connecting the cities. And the weights in this case are the distance between the cities. So in routing, however, the cost of an edge has a different interpretation and different routing protocols, and we can assume that there is a cost associated with each edge. If there is no edge between the nodes, the cost is infinity. Now let's see how internet is modeled as a graph, which is shown in this diagram, the weighted graph. So each A, B, C and D and E, F are the nodes, and the lines connecting these two nodes are called edges, and the number which is represented above the line are the weight. Right. Now let's move on to least cost routing. When an internet is modeled as a weighted graph, one of the ways to interpret the best route from the source router to the destination router is to find the least cost between the two. And you can say that the source router chooses a route to the destination router in such a way that the total cost for the route is the least cost among all possible routes. So now let's see an example, and the best route between A and B we have to find. And according to this diagram, it is between A, B and E, which connects the nodes A and E. Okay, and the total cost of AB is 6, and this means that each router needs to find the least cost route between itself and all other routers to be able to route a packet using this criteria. And the least cost trees for a weighted graph can have several properties if they are created using consistent criteria. The least cost route from X to Y in X trees is the inverse of the least cost route from Y to X in Y tree. And the cost in both directions is the same. For example, if you take the route from A to F, you can move from A, B, F, E, F, but the route from F to A is F, E, B, A, which is the inverse of the first case. And the cost is 8 in each case. So instead of traveling from X to Z using X tree, we can travel from X to Y using X tree and continue from Y to Z using Y tree. For example, if we can go from A to G in A tree using the route A, B, E, F, G, we can also go from A to E in A tree, that is A, B, E, and then continue E tree using E, F, G. And the combination of two routes is the second case is the same node as in the first case. The cost in the first case is 9 and the cost in the second case is also 9, that is 6 plus 3. Now let's move on to some of the routing algorithm. And the first routing algorithm which we are going to see is about the distance vector routing. Routing table can be either static or dynamic. A static table is one with the manual entries, and a dynamic table on the other hand is one that is updated automatically whenever there is a change somewhere in the internet. Today, an internet needs dynamic routing tables. The tables needs to be updated as soon as there is a change in the internet. For instance, they need to be updated when a router is down, and they need to be updated whenever a better route has been found. So routing protocols have been created in response to the demand for dynamic routing tables. A routing protocol is a combination of rules and procedures that lets routers in the internet inform each other of changes. It allows routers to share whatever they know about the internet or their neighborhood. The sharing of information allows a router in San Francisco to know about the failure of network in Texas. So the routing protocols also include procedures for combining the information received from other networks. And we have different types of routing protocol, that is intra and inter-domain protocol. So in distance vector routing, the least cost route between two nodes is the route with the minimum distance. So in this protocol, as the name implies, each node maintains a vector or table of minimum distance to every node. The table at each node also guides the packet to the desired node by showing the next strip in the route. You can see in the example. We can think of the nodes as the cities in the area, as I said earlier, and the lines as the roads connecting them. And a table which can show the tourist with a minimum distance between cities. What is, you can see here, right? So the table for node A show how we can reach any node from this node. For example, our least cost route to reach node E is 6, and the route passes through C. And tables are stable. Each node knows how to reach any other node and the cost. At the beginning, however, this is not the case. Each node can know only the distance between itself and the immediate neighbors and those directly connected to it. So for the moment, we assume that each node can send a message to the immediate neighbors and find the distance between itself and these neighbors. And the initial table will be only it knows the distance between themselves and the immediate neighbor. And the distance for any entry that is not a neighbor is marked as infinite here. And the whole idea of distance vector routing is the sharing of information between neighbors. Although node A doesn't know about node E, node C does. So if node C shares the routing table with A, then node A also know how to reach node E. On the other hand, node C doesn't know how to reach node D, but node A does. So if node A shares its routing table with node C also knows how to reach D. So in other words, nodes A and C as immediate neighbors can improve their routing table if they help each other. There is only one problem, and how much of the table must be shared with each neighbor. And a node is not aware of a neighboring table. The best solution for each node is to send the entire table to the neighbor and let the neighbor decide what part to use and what part to discard. However, the third column of the table, that is next stop, is not useful to the neighbor. When the neighbor receives a table, this column needs to be replaced with the sender's name. So if any of the rows can be used, the next node in the center of the table, and a node therefore can send only the first two columns of its table to any neighbor. In other words, sharing here means the sharing only the first two columns. When a node receives a two-column table from a neighbor, it needs to update its routing table. So here updating takes 3 steps. In the first step, the receiving node needs to add cost between itself and the sending node to each value in the second column. So the logic is clear here. If node C claims that its distance to a destination is X and the distance between A and C is Y, and then the distance between A and that destination via C is X plus Y. And the second step is the receiving node needs to add the name of the sending node to each row as the third column if the receiving node uses information from any row. The sending node is the next node in the route. And the receiving node needs to compare each row of its whole table with the corresponding row of the modified version of the received table. Thank you.